Good morning, everyone. First of all, I want to thank all of the participants for this wonderful organization. So our first speaker is İzel Avkan. She's from the Middle East Technical University, and she will talk about mysteries of the prime number. More specifically, number theorem. İzel, the floor is yours.
Thank you. Good morning, everyone. My name is İzel Avkan. I am a senior mathematics student at the Middle East Technical University, as Yalçın said. Today, I'm going to talk about what is analytic number theory and prime number theorem, which is an important theorem that analytic number theory studies. Here is my outline. Firstly, I will give definition of analytic number theory and talk shortly about its history. Then I will move on to prime number theorem and talk about what does it claim and what are the sum of its equivalent forms and the outline of its proof. And lastly, I will talk about some open problems in analytic number theory. So let's begin with the definition of analytic number theory. It is a branch of number theory that uses techniques of analysis to solve problems about integers in general and primes in particular. It became an independent part of number theory during the 19th century when works of Kılıç and Riemann showed that methods from complex analysis can be used to study distribution of prime numbers. Now, having an idea what does analytic number theory study, we can look at prime number theorem, which is a specific example of it. Firstly, let me introduce the prime counting function, p of x, which gives the number of primes less than or equal to x. Prime number theorem first appeared in 1798 as a conjecture by the French mathematician Adrien-Marie Legendre. On the basis of his study of a table of primes up to 1 million, Legendre stated that if x is not greater than 1 million, then x over log x minus 1.08366 is approximately equal to p of x. And this result, indeed, with any constant is an equivalent form of prime number theorem, which says the result for constant being equal to 0. On the other hand, apart from Legendre, Gauss also studied the asymptotic behavior of p of x, and he stated that p of x is approximately equal to integral of 1 over logarithm of t from 2 to x. But he never published his results, and today we have prime number theorem stating that p of x is asymptotically equal to x over log x. So what does this asymptotically equal mean? It means as x goes to infinity, limit of p of x divided by x over log x is equal to 1. And prime number theorem proved in 1890s, almost a century after its conjecture by Hadamard and de la Valle-Puissin independently. Moreover, I would like to show some graphs to see if the computational evidence support the prime number theorem. In this figure, you can see graphs of 4 different functions. It is p of x, L of x, which stands for the logarithmic integral, and it is Gauss approximation. X over log x, it is what prime number theorem claims, and finally Legendre's approximation. From this graph, it may be seen that x over log x is not a good approximation as the others. However, note that this graph only has x values up to thousands, which is a very small number when compared to infinity. Therefore, from this graph, we can only conclude that all 3 graphs approach to p of x, but at different rates, and apparently x over log x has the smallest rate. And in this figure, you may think that there is just one thick line after x is equal to 1000. However, it includes all the 4 graphs discussed in the previous figure. And in this case, x values are up to 10 to the 7, which is a greater value when compared to infinity. And as you can see, in this case, all 3 graphs are closer to p of x. So in this case, we can say that actually all these 3 approximations, all these 3 suggestions are good approximations for p of x. Now, having an insight that prime number theorem looks like true, let's look at the first steps in the direction of the proof done by Chebyshev. First, he showed that if limit x goes to infinity, p of x divided by x over log x exists, then it must be equal to 1. However, he couldn't prove the existence part. Then he showed that there exists some constants a, b greater than 0 such that p of x is bounded below by ax divided by log x, and it is bounded above by bx divided by log x for all x greater than or equal to 2. And he showed his claim by using the elementary properties of the binomial coefficients. And all the evidences suggested that a and b were getting closer and closer to 1. However, as they get closer to 1, the proof becomes more and more technical. So before moving on to proof of prime number theorem, I would like to show some equivalent forms of it, which gives alternative ways of proving prime number theorem. Firstly, let me introduce some analytic functions. This is one Mangold function, which takes the value of logarithm of p if n is equal to p to the alpha, where p is prime, and 0 otherwise. Chebyshev function is the sum of one Mangold function for n less than or equal to x, and theta of x is the sum of logarithm of p for p less than or equal to x. And here you can see 3 claims which says that which gives them equivalent forms of prime number theorem. For instance, this says that prime number theorem is equivalent to theta of x being asymptotic to x, or p sub n, where it is the nth prime, is asymptotic to n times logarithm of n, or Chebyshev function being asymptotic to x. So showing any one of these 3 claims actually proves the prime number theorem. And today I'm going to show Chebyshev function being asymptotic to x in order to prove the prime number theorem. So now we are ready to move on to proof of it. Actually, its proof contains many technicalities and it is quite long to explain in 20 minutes. So I will just give the outline of it. And if you want to read the detailed proof, you can refer to my reference list. Here we have some analytic functions. I talked about one Mangold function and Chebyshev function. And this is Riemann zeta function. It is a complex valued function, sum of 1 over n to the s for n 1 to infinity, where s is equal to sigma plus it. And the outline of the proof starts with an equivalent form of prime number theorem. As I said, today I'm going to show that Chebyshev function is asymptotic to x to prove prime number theorem. Here you can see an important lemma which states that the differentiation, the formal differentiation, gives the correct result. And here if we substitute one Mangold function for an, then by definition ax would be Chebyshev function and a1 of x would be Chebyshev 1 function. So if we can show that Chebyshev 1 function is asymptotic to x squared divided by 2, then by using this lemma, we can say that Chebyshev function is asymptotic to x. So our new claim is to show that Chebyshev 1 function is asymptotic to x squared divided by 2. And here, after skipping some details, for c greater than 1 and x greater than or equal to 1, we have the following equality. And we want this equality to hold also for c is equal to 1. And to do this, we need to study the zeta function in the neighborhood of the line sigma is equal to 1. And actually, this is the most technical part of the entire proof. Studying zeta function includes finding the upper bound of zeta function and its derivative, and finding where its zeros exist and doesn't exist. And the main aim is to show that it doesn't have any zeros on the line sigma is equal to 1. So after showing that, we have f of s is analytic at s is equal to 1. Also, it is clear that this function 1 over s times s plus 1 is also analytic at s is equal to 1. So h of s, being product of 2 analytic functions, is also analytic. Here you can see our new claim. So let's look at its proof. The integral of x to the s minus 1 times h of s, it is actually this integral, but with not this boundaries. Instead, around the rectangle R, this rectangle is denoted as R, and this integral is equal to 0 since the integrand is analytic inside and on R. We know that h of s is analytic from the previous discussion, and also x to the s minus 1 is clearly analytic. So again, we have a product of 2 analytic functions. And also one can show that integrals along the horizontal lines tend to 0 as t goes to infinity as well. So the overall integral is equal to 0, and the integrals along the horizontal lines are equal to 0. So we must have integrals along the vertical lines must be equal to each other. And this is the mathematical formulation of it. And on the line sigma is equal to 1, remember sigma was the real part of S. We can write S as 1 plus IT to obtain the following equality. Here, if we write 1 plus IT, then 1's will cancel out. And x to the it can be written as e to the it times logarithm of x. We just use the simple properties of logarithm. And here we just write 1 plus it, and this is the imaginary part of this integration. So we get what we want, and hence this completes the proof of the claim. Also, one can show that this integral converges. Then by using Riemann-Lebesgue's lemma, which states that if this integral converges, then this integral is equal to 0, we deduce that the right-hand side of the claim is equal to 0. So after some easy mathematical computations, we get that Chebyshev-1 function is asymptotic to x squared divided by 2. And by using the lemma about differentiation, we get Chebyshev function asymptotic to x, which was an equivalent form of prime number theorem. Hence, this finishes the proof of prime number theorem. Actually, this is analytic proof of it. It means it contains methods from complex analysis. Also, there is another proof called elementary proof, which uses number theoretic methods. But today I wanted to focus on the analytic proof of it. So prime number theorem is one example of what does analytic number theory study, and it is proven. But what about the unsolved problems? Before ending my talk, I would like to give some open problems in analytic number theory. The first one is famous Riemann hypothesis, which is in the list of $1 million Millennium Prize problems of Clay's Institute. Let's recall the function one more time. It is the sum of 1 over n to the s for n1 to infinity, and this function converges absolutely for real part of s greater than 1. Here you can see a graph on the x-axis. It is labeled as sigma, and the vertical axis is labeled as t. And this region is defined as the critical strip, and this region is where sigma is between 0 and 1, and t goes to infinity in both directions. And zeta function has two types of zeros, trivial zeros and non-trivial zeros. Trivial zeros are those that lie outside the critical strip, and non-trivial zeros are zeros that lie inside the critical strip. Well, we know that trivial zeros at negative even integers, and we know that there are no zeros on the line sigma is equal to 1 and sigma is equal to 0. However, we don't know the exact locations of the non-trivial zeros, and Riemann conjectured that they lie on the line sigma is equal to 1 over 2, which is known as the critical line, just in the middle of this critical strips. And also, Riemann hypothesis has many equivalent forms. And today I want to talk about the one which is related with the prime number theorem. Remember, this is our prime counting function, and this is logarithmic integral. It is Gauss approximation for it. And this equation says that Riemann hypothesis is equivalent to say that the error term in the Gauss approximation is bounded by the square root of x times logarithm of x. So proving any one of these, so if we prove Riemann hypothesis is true, then this will be the case, or vice versa. And so why it is important to prove Riemann hypothesis? Well, because it will give significant results on the distribution of prime numbers, like predicting exactly where the end prime is, or finding the distance between two consecutively large primes, because individual zeros determine correlations between the positions of the prime. So proving prime number theorem will help us to figure out the mystery about prime numbers. And lastly, I want to talk about Meritense conjecture, which is a striking example of a mathematical conjecture proven false, despite a large number of computational evidence in its favor. Here you can see Möbius function. For n is equal to 1, it takes the value 1. And if n is greater than 1, we can write it as its prime factorization. And if all the alpha i's are equal to 1, then we have mu of n is equal to -1 to the k and 0 otherwise. So Möbius function can only take three values, -1, 0, and 1. And this is Meritense function defined as the sum of Möbius function for n less than or equal to x. And it is clear that m of x is less than or equal to x, because even if mu of n takes the value for all n, then there are x values, so x times 1, it can be maximum 1. However, it will have also -1s and 0s on the way, so actually it must be less than x. And Merten's conjecture is about the non-trivial upper bounds for m of x. And he claimed that absolute value of m of x is less than or square root of x. And actually this was the case for a very large number of x values. When we try to disprove something, it is an easier way to find a counterexample to disprove it. However, in this case, they couldn't find an explicit counterexample. Instead, they found an interval where it lies, and it is above 10 to the 16. So actually, this holds for x 10 to the 16. However, as I said, they couldn't find an explicit counterexample. But Otliosko and Teriel disproved Merten's claim in a different manner. They defined a new function, small m, as ratio of big M and square root of n. And if this small m is between -1 and 1, then Merten's conjecture will be true. However, they showed that limit of infimum of m is less than -1, and limit of supremum of m is greater than 1.06. So this says that Merten's claim was wrong, and it is not less than or equal to square root of x. And we still don't know the true rate of growth of m of x. All we know is that it is some power of x, where this power is between 1/2 and 1. And this is the mathematical formulation of this. And this is big O notation. It says that there exists some constant k such that absolute value of m of x is less than or equal to k times absolute value of this equation for all x. So this is what I want to talk about Merten's conjecture. To sum up, today I tried to explain what does analytic number theory study, and it studied the growth rate of some analytic functions to find the distribution of prime numbers. Then I talked about prime number theorem, which says that p of x is approximately equal to x over log x. And finally, I talked about some open problems in analytic number theory, particularly Riemann hypothesis and Merten's conjecture. Thank you for your kind attention. For those of you who are interested, here is my reference list where you can find the detailed proof of the prime number theorem. And if you have any questions, I would like to answer them.
Thank you, İzel, for a wonderful talk.
Thank you.